Welcome to Study Loop.
This problem asks about the stability or unstability of the beryllium-8 isotope. The important thing to know in problems of alpha decay like this is that a nucleus will be unstable if the mass of the parent nucleus is greater than the combined mass of the daughter nucleus. That's what it decays into, and the resulting alpha particle. So we can write that or think of that in terms of binding energy. In the case of when the assembled nucleus or atom is greater than the combined mass of its constituents, in that case, the binding energy is going to be negative. So, in terms of binding energy, when it is negative or less than 0, that means the parent is unstable. And the converse case, when the binding energy is positive, the parent nucleus is stable. So let's plug in relevant masses and find the binding energy. The reverse of that is what they call the disintegration energy. Let's instead find the binding energy here, because that is more in line with what we're so familiar with so far. So the case of binding energy, we take the combined mass of the individual constituents of the reaction. In this case, that is going to be that's going to be 2 alpha particles. And we're going to subtract from that the assembled parent nucleus, the atomic mass, that is. And we write that symbolically as 8Be. And to make it in units of energy, we're going to multiply this difference by the conversion factor of 931 mega electron volts per atomic unit. We plug that in, and we find that there's a binding energy of negative 0.9, oh, I'm sorry, 0.09 221 mega electron volts. And from what we said above, if we have a negative binding energy in this case, it implies that the parent is unstable. So as the problem asked, let's just write out the actual compound here. Our beryllium atom, or our beryllium isotope, Be8, is unstable. And that's our answer. Now for part B, it asks us to assess the stability of carbon-12, and specifically if it will decay into 3 alpha particles. If we look up the atomic mass of carbon-12 in our Appendix B, we find that it is exactly 12. I believe it's the reference used to set all atomic masses, hence its lack of fractions. And we will compute the binding energy here. In this case, I have computed the, we'll do the problem over again because I was originally doing this in terms of disintegration energies, and that's not how we want to formulate this problem. So let's get rid of that. We're going to compute this in terms of binding energy, and that is the combined mass of the constituents, which is 3 atomic masses of alpha particles minus the atomic mass of carbon-12. And we are going to multiply that, because right here we have units of mass. We're now going to multiply that by the conversion factor to units of mega electron volts. And doing that, we find the binding energy, in this case, is positive 7.27 408 mega electron volts. And since this binding energy is positive, carbon-12 will not decay into 3 alpha particles. It is stable. And that is the answer to our problem. Okay.